Hi everybody, lucky you, another video. So I've started up a new RStudio session here, and I've set my working directory so that things work for me, and hopefully you're set up the same way. Now up to this point we have inputted data directly into the console, through the combine function, and we've inputted data through a script basically the same way, but in reality neither of those are very practical in terms of bringing in big data sets. And so in this video, I'm going to walk through example 2 in Lab1, and in that example, we're going to import a comma-separated values file, a text file of data. This is something that you could export easily from Excel. And we're going to import that into RStudio and then play with it a little bit. So the first thing I want you to do, we're going to take advantage of RStudio's import dataset function, and that's up here in the session pane. All these, it's such a pain. The session pane, and this is the import dataset. So I'm going to click here. I'm going to import from a text file, and it goes right to my working directory. We are in Lab1. And we're working on example 2. So Lab1, example 2, and this is CSV file, this comma-separated values file. Double click there. And what you'll see is this dataset import window pops up. And it's nice because it shows you this top space shows you the input file as the text file that it is. And then below it is a preview of how R is going to interpret that text file. Now, first thing, you want to give it a name that you don't mind referring to over and over again in your script. And in the script that I wrote for the analysis of this data, I called the dataset extract.dat. And you'll notice what I do is I often put a suffix at the end of all of my variables to give me an idea of whether it's a dataset or a model or something like that. So you'll see .dat on a lot of stuff that I do just so I know that it's a dataset. This particular data set does have a header row, so I've clicked yes, and in that header row are the names of the two columns. We have sample IDs and extract values. The separator is a comma, so that's good. Decimals are indicated by a period. That looks great, and the data frame visualization looks pretty good. If all that looks good to you, you can go ahead and click import. And what you'll see immediately is that you have a pane pop up above the console. This is where we were working with scripts before. This is also the place where you get kind of an Excel-like viewer of data sets that are in working memory. And it pops up, and again, it looks good. I can't stress enough how important it is when you import a data set that you look at it and make sure that it is imported correctly. A function that we will use a lot, so I'm down here in the console window, is str. This is a structure function, and you can feed it different objects. I want to ask R what it thinks the structure of extract.dat is. And you'll see R says, well, that's a data frame. That's R's language for essentially a data set in the form of a matrix or a table. And it has 14 observations of 2 variables, and those variables are sample ID, that's great, and that's 1 to 14, and it has extracts that are numeric values. So it looks like everything loaded correctly. Once you have the data set of interest loaded into working memory, then you can start working on it. You can either create a new script and program specifically what you want to do. I, of course, have written a script for you already, so let's go ahead and open that one up. I'm going up to File here. I'm going to Open File, and again, we are in Lab1. And we are in exercise 2, or example 2, and this time we're looking at the R file. This is a script file for R. I'm going to double click that, and you'll see it pop up immediately in the script pane. And now you'll see we have 2 tabs open in the script pane. One tab was the data set, and now we have the script. I'm going to go ahead and get rid of the data set because I get distracted by shiny objects, and I'm going to get rid of things that we're not specifically using right now. Okay. Now, the first thing you'll notice here is that I have a bunch of lines starting with hash marks. Again, this is my annotation to you to sort of orient you where we are, and also to give you a sense of what the script is all about. The first real line in the script is line 8. This is this QQnorm function. What I want to do is I want to ask R if the 14 extract values if they come from a normally distributed population. And the way I want to do that is through a Shapiro-Wilk test. And if you'll remember from lecture, what a Shapiro-Wilk test does, it essentially asks whether the correlation that you get from a quantile-quantile plot significantly deviates from a straight line with slope 1 or not. And that's going to tell you whether or not it was likely that the sample came from a normally distributed population. And R makes the visualization of a Shapiro-Wilk test really easy through this QQ norm function. And what you want to feed the QQ norm function is a set of numbers. So I have a sample, and the way I get the 14 numbers in my extract column here, let's look at the data set again. I'll click on it over here in the session pane, and it'll pop up there again. What I want to do is I want to ask if the 14 numbers in the extract column are normally distributed. And the way I specify a column within a data table, within a data frame, is by using this $sign. So I say the name of the data set, extract.dat, follow it by the $sign, and then the name of the column. And what that's going to do is going to specifically isolate those 14 values in that column. So that's what I want to know, is whether it's normally distributed. Everything after that, all these other arguments within the QQ norm function, these are all graphical formatting arguments. The PCH is going to tell me how big the dots are in the scatter plot. The color is what color they're going to be. You can assign titles, axes, labels, all this kind of stuff. R is really phenomenal, both in its graphical aesthetic, its kind of base graphical aesthetic, but also in its ability it gives you to customize everything. So technically, all these arguments are not needed for what we're doing, and over the course of the semester I'll be throwing more and more sort of graphical parameters at you, and you can spend a lot of time playing with that. But if we run this line, QQ norm, on the extract column, I'm going to send it to the console. Again, command return for me on a Mac. Boom, what you see pop up over in the management window under the plots tab is that scatter plot. Wonderful. And if I want to see how these points relate to the line of slope 1 that I would expect if the sample were perfectly normally distributed, I can run this line over here, line 9 in the script, QQ line, on the same set of 14 numbers, and it overlays a line on top of the plot. So what you see here is that these lines are actually hug the expected correlation line pretty tightly. So I would expect if we were to run a statistical test that we would have a hard time concluding with any sort of confidence that these came from a population that was not normally distributed. Well, the way we run that test is here on line 12. We run the Shapiro.test function. And again, we run it on the same 14 values, extract.dat, $extract. I'm going to send that to the console, and instead of something popping up in the plot window, we get the output popping up here in the console. It ran a Shapiro-Wilk normality test. It used this data, the extract column, that's perfect. And it's giving me essentially a correlation of the points around this line that's very, very high, very close to 1. It's 0.95, and you'll see that the p-value associated with that is also quite high. In other words, this is a scatter that one could expect quite often from a sample taken from a truly normally distributed population. In other words, we have no evidence to reject the null hypothesis or to reject the idea that these data are normally distributed. So if we were going to be running a test that assumed normality, we seem to have satisfied that assumption. Now what follows here throughout the rest of the script are a couple other lines that are useful, and it's just kind of I'm just sort of throwing them out at you so you can get a sense of a little bit of the base functionality of R. Hist, you can imagine, is going to be a histogram of that same data. I'm going to send that to the console. It again pops up in the plot window. Now that last quantile plot that we made is not gone. It's just kind of on the previous page. And so if you go to the arrow here, you can go back to it, or you can go forward to the histogram. If any of these plots you wanted to export into a report or into a paper or do anything with, it's very easy. You can go to export, You can save it as an image, you can save it as a PDF, or you can copy it directly to the clipboard and move forward with it. So it's very nice. So there's the histogram function. We also have a summary function. If I wanted to get some summary statistics on those 14 numbers, throw it to the console, and it's going to give me the minimum, the maximum, the median, the mean, and boundaries of the quantiles. Box plot is going to do exactly what you think it should. It gives you another plot. Notice I don't have any titles anywhere, and that's because I didn't add any of those graphical parameters at the end of this box plot function. But this is giving you the spread, kind of a box and whiskers plot of those 14 values. The last thing I want to show you in this script are lines 22 and 23. It's starting to get into some hypothesis testing about this particular sample. So the first hypothesis test that we could run is a simple t-test. Now, we only have one population, and so when you run a t-test on a single sample, you're clearly not asking if the sample is different from another sample because you only have one sample that you're dealing with. So what you'd set as the null hypothesis in a single sample t-test is some hypothesized true population mean. And so here I'm setting mu to 78. And when I run this t-test, what I'm asking is it likely that this particular sample was randomly pulled from a population whose true mean is 78? So I'm going to run a t-test on those 14 numbers, and that is the question that I'm asking. And if I send that line to the console, it's going to give it to me. It's going to calculate what the associated t-value is under this particular hypothesis. So you'll notice my mean of my sample is 75. That is quite a bit below 78, and that's why I have a very a negative t-value that's quite high in absolute terms. When I construct a 95% confidence interval about that mean, it ranges from 75.3 to 76.7. This 95% confidence interval does not contain 98. So I know that I'm at least 95% confident that 78 is not the true value of the population this sample was taken from. And now if you look at the p-value, it's incredibly low. I would conclude from this, I would reject the null hypothesis. The true mean of this population is not equal to 78. You can also run, you can also find what the power was of that particular t-test. Now, it won't be surprising because we had such significance. We clearly had sufficient power to detect significance. So if you were to ask the power of that particular t-test, we're going to probably find that it was quite high. And let me open up the window here a bit so you can see all the parameters of power. So when you run a power of the t-test, you need to specify how many individuals are in the sample. Well, so I can set n equal to the length of the column of numbers that I'm giving it. Delta, this is my detection difference. That's going to be 78, which is the null hypothesis, minus the mean of mine. So this is the detection difference that I'm going to be putting in to the t-test for the power calculation. I can tell it what the standard deviation is of my particular sample. I can specify my type 1 error rate. So this is my alpha of 0.05. It is a one sample t-test. I'm running a two-sided test, and strict equals true. And I can't remember offhand what that refers to. I'll look it up and we can talk about it if anyone's interested. But when I run this particular function, we get exactly what you would think. It recognizes everything we told it. We have 14 samples. This is my detection difference between 75.94 and 78. I have a standard deviation of the sample. I've specified my alpha, and here we see that we had a power that was almost equal to 1. So that agrees quite well with the highly significant result of the t-test that we ran. Okay, that's about it. I'm hitting the 15-minute limit on this. There are a couple other things in the Lab1 handout after this that you should take a look at in terms of how to get help in R, a little bit on package installation and management, but you should be good to go. Thanks a lot.